there's a minus here, so the slope, the activation energy must be positive, the rate constant of course is positive, so overall this slope is negative. So your line must slope down. If it doesn't slope down, you know you're making a mistake. It must slope down, and what you're after is the intersect with the y-axis. So you plot a graph and you look for that intersect. Now it's possible, I don't know how mean this question is, but it's possible that you're going to get a graph where the line extrapolates to cut the y-axis miles up here, and it's going to be difficult to plot. And if that's the case, then what you're going to do is you're going to have to find the slope of the line, and that will give you the activation energy. And then you can use the data, because you now know the activation energy, you know R, you can use the rate constant and temperature to calculate this intercept. I shouldn't think it's that mean, but it could be. Okay, questions? Arrhenius plots, very, very common questions for not just this, but next year's practical. So you need to be able to do Arrhenius plots at the drop of a hat. Okay, and that's the physical that's the kinetics for that paper. So let's move on to the next paper. So this one is hang on, what's that? Oh, that was the research, right. This is the paper which I hope is the one that is on Learning Central for you. And again, 2 questions from kinetics. Question 2, define what is meant by the term homogeneous catalysis and how it applies in ozone hole-related chemistry. So this must be something that, I don't know if Mike covered it with you this year, but it was covered last year. Homogeneous catalysis, first of all, that's when a catalyst is in the same phase as the reactants. So the classic example of that are enzymes in the body, which are in the aqueous phase, along with the molecules that they're causing to react. Other examples are metal complexes that are dispersed within aqueous or other solvents. And what's special about them is that every molecule for your homogeneous catalyst, every molecule can act as a catalyst. Whereas with a heterogeneous catalyst, your catalyst is a lump of, could be metal, could be oxide, might be very small, maybe it's nano dimensions, usually nano dimensions, but that's still 10,000 atoms or more within your lump, and only some of those, only the ones at the surface, are going to be active. Obviously the ones in the centre can't. So you get, by moving from homogeneous to heterogeneous, you reduce the number of active sites hugely. Heterogeneous catalysts have other advantages. They're much easier to use than homogeneous. You can separate them away. But that's a little bit more information than you need. How it applies in ozone hole-related chemistry. I think this means the halogen radicals, chloride and fluoride ions, which in the gas phase cause ozone to break down, but then the radicals remain there as radicals or are regenerated in the reaction. So it's a homogeneous reaction because it's all in the gas phase. The chloride, the halide ions are there as catalysts and they're regenerated during the reaction, but they degrade the ozone. So I think that's what that's about. Okay, question 6. A catalyst results in an increase in the rate of reaction by 100 times. I think we've seen this one before, haven't we? Let's do it again anyway. Okay, so we're going to have K1 is going to be equal to, no, hang on, let's do that as K2 is equal to 100 times K1. At 200 degrees C this time. I'm not going to write Celsius. I know I had to do my calculations in Kelvin, so that's going to be 473 Kelvin. calculate the decrease in the activation barrier for the reaction that the catalyst induces. Okay, once again, we're going to be using our ratio K1 over K2 is equal to e to the minus EA1 RT divided by e to the minus. You see how I don't remember the derived equation, I just remember how to do it. If you want to remember the derived equation, absolutely fine. And we simplify all that, and we end up with log K1 over K2 is going to equal minus 1 over RT into EA1 minus EA2. I think that's right. And now again, it's just a question of putting the numbers in. This is the log of 1 divided by 100. Minus 1 over, we've got 8.314 times 473 times this difference in activation energy. If I multiply everything by 8.314 times 473, and I get 8.314 times 473 times 1 over 1, times the log of 1 over 100. I'll bring the minus over there as well. And that's equal to our difference in activation energy. And when you work out this number, you'll find it equals, find it? Well, I make it 18.110 joules per mole, which is 18.11 kilojoules per mole. You can always express, if you write it like this, that's fine. But you'd always express an activation energy in kilojoules per mole. Find part B. Use the following data to plot a graph to determine the rate constant for the reaction involved, and hence determine the pre-exponential factor, given the information that this is a first order reaction running at 23 degrees C with an activation barrier of 50 kilojoules per mole. Okay, this is a question I come across very often. So, write down the important points. We've got a first order. We know the activation energy, 50 kilojoules per mole. And we know the temperature is 23 degrees C, which is 296 Kelvin. Again, just change to Kelvin straight away. Don't mess around with it. What we're trying to find, we want to know the pre-exponential factor. So it's A that we're trying to find. First of all, we have to find the rate constant. Plot a graph to determine the rate constant.